Hi guys, this is Ratnesh and today I'm going to discuss basics of ASR 9000. You can see in your screen, this is the PPT I'm going to discuss today, and I have a lab topology as well, and this is my lab topology. So once I will go through the basic concepts of ASR. After that I will come to this topology, and I'm going to configure OSPF on this platform. So ASR is nothing but one type of ISP router. This is aggregate service provider router. You can see different type of iOS train that Cisco has: iOS, iOS XE, and iOS XR. Now today the focus is iOS XR. Probably you may know about this iOS and iOS XE. Uh, Let me give you a small notes on this iOS and iOS XE. So iOS is obviously it is operating system related to network. This iOS is something like monolithic type of operating system, means you have single, you can say, the management OS, and whenever a query come to this, any query packet, means this iOS management has to take decision. Means inside this operating system, inside this iOS, you have all the things. Whenever a query will come, entire iOS is responsible for that query. Now next, Cisco has introduced this iOS XE. You will find this in ASR 1000 and 4500, plus you will find in 3850 series. iOS XE is nothing but the Linux kernel, and in 4500 and 3850 you have some wireless plugins as well. Means you can use these devices as wireless devices as well. So iOS XE, if you see iOS XE in 38500, you have bundle mode and install mode. The whole idea about this iOS XE that you have multiple processes that is running inside the operating system, means you, for different features, you have different patches, and those patches or daemons are again mapped with the iOS. So iOS XE is not monolithic type of uh, operating system. It is like modular than iOS. Now next is this iOS XR. That today I'm going to discuss about this, the architecture and the hardwares of this ASR 9000. This iOS XR is again Linux iOS, and you can see this is 80% similar to Nexus iOS. So whatever you have in Nexus, Nexus is again one type of Linux iOS. So whatever you have in the iOS XR, you have the same type of features in the Nexus as well, with some exceptions. And 50% of hardware is same of this ASR 9000 with the Nexus 7K or maybe Nexus 9K. That I will show you today. I'm going to show you. So that is a small thing about this. Let me go to other slide. Okay, again this is the thing. Here you can see there are different type of processes. So once I will start with the architecture of this particular platform, you'll come to know what is RP, what is RSP. I have devices here in the lab. Suppose I am on router number 1, that is top here, and it is asking for username and password. So suppose Cisco is my username password. Now you can see on your screen that the same type of thing that we have seen in the slide. So you can see RP, then /0, then /0, then slash the name of the CPU 0, and then the name of the router. So this is the name field. Sorry, this is name field. I'll show you that. Let me go back to the slide. What does it means? Come to know here. RP is the route process. RSP is route switch process. Now the whole idea behind this particular platform is to create such type of a router or create such type of switch who will do hardware forwarding. So entirely this platform, that is the ASR 9000, is doing the hardware uh, forwarding, but it is not true. It is not 100% true that all the time they are doing 100% of hardware forwarding. I will explain you in the upcoming slide that how they are forwarding the packet. But yeah, most of the time they are doing the hardware level forwarding, and for that they have this architecture here for RP0 CPU. You may have CPU 0 and you may have CPU 1. And what is the architecture for these CPU? Again, I have to cross some slides. I have the slide. I'll show you the slide at what I am talking about this hardware. Yeah. So this is the overall chassis design for this ASR. You can see here that the line cards, they are mapped with both the CPU. So they are mapped with the CPU 0 and CPU 1. This line card is mapped here, and one trace is going to the CPU. So suppose this is 0, this is 1. You can see here, this is routing switch process, that is the RSP. So we have RSP 0 and we have RSP 1. Again, this is because they have redundancy behind the scene. Means behind the scene, this is completely hardware architecture. And when I come to the software architecture, I'll come to know. But yeah, whenever a packet will come here, now obviously the first trace or first packet will go to CPU. Either it will go here or it will go here. Once the supervisor engine, in this case the RSP engine, once RSP engine figure out where to send that particular packet, then they will respond to the other line card. So all these things will programmed, and next time they will not ask. So next time they will go like this. So there are chances that packet will come and go within the module. There are chances that packet will come to one module and it will go to other module. So both the case, first packet will go to the whatever the decision maker, in this case the RSP is the decision maker, and after that they will do all this forwarding with respect to line rate. Let me go to the second slide. So you can see there the naming format of this particular platform, and I'll show you that we can change something here. So here, suppose if I want to assign some name, so the same thing we have in the normal iOS, that is the host name. Suppose this is my router number 1. If I type here router number 1, still you can see in your screen that still it is showing iOS. So likewise in Juniper, we are doing the commit. Here also you have to do commit. So once you will do the commit, then you will see that R1 will replace iOS. Before doing the commit, if I do show configuration, it is telling that this is the command you want to commit, or this is the command. If you commit it, it will execute. So if I commit this command, and now if I check show configuration, maybe the font size is a bit small, so now it is not there, because you can see instead of iOS, that is replaced by R1. So this is one major change in the structure of this platform, that whenever you are executing something, you can commit, you can roll back, you can commit, you can replace your commit, like that. So these type of features we have in this platform. Okay, this is the topology I'm going to configure today, and what I'm doing here, that I'm covering some theoretical things, and then I'm showing you the topology. So it's very much similar to iOS features. Like suppose if you're running OSPF daemon, so same OSPF daemon, whatever the program, will be used inside iOS. Same will be used inside iOS XE. Same will be used inside iOS XR. So the program will be the same. The only difference is that how different type of operating system they are calling inside their main program. So in this program, they are calling in some different way. In this program, they are calling in different way. In this program, they are calling in different way. In NX OS, they are calling in different way, but for all the daemons in the NX OS, you have different type of logging, you have different type of debugging and all these things. So separately, you can monitor or track all the OSPF features in Nexus OS. Even in iOS XR also you can do that. Means the operating system can do that. Okay, I'm here. So today's session I'm going to explain you. We have different areas like area. You can see that 10. This is the backbone 0, and this is the 20. Now, if you run the same thing with the same IP address, everything in the iOS, you'll get the same result. So what is different here in terms of configuring it? Configuration is different in this platform, and how they are calling those things inside the operating system, that is different. So these things we have to understand, but the result will be the same, means the output will be the same. So in case of OSPF, you know that you have O, you have OIA, you have OE1, all these things like NSSA, all these things will be the same. Means the technology is the same, syntax and how they are calling inside the OS is the different. Okay, these are some slides just to increase the number of slides. Okay. Now, this platform will give you high availability, and we have seen the architecture of the XR, that inside we have CPU 0 and 1, and these CPUs are mapped with the line cards. So they are mapped like that. So that's why this is highly scalable and this is highly redundant. You have different features here, like you can do in software upgrade. I don't know, ISS, in service software upgrade, ISU or FSU. You can do it. You have non-stop forwarding. This feature is very enhanced in this platform. You have separate control and data planes. Now this feature is common in all this platform. Most of the devices you have separate control and data plane. You have RP and DRP redundancy. You can see here, and I'll show you again in the slide. So one of the core is what is acting as a active, other core will be acting as a standby, and we have some other features as well. Now this feature is also important, the last one I'll show you in the slide as well. So let us see this thing, RP and DRP redundancy feature, why they are like this. So the architecture behind the scene is like that, that one of the core all the time they are in the active and other core is in the standby process. So if you type this command, the first command you want to check in the switch is the show redundancy. In Catalyst 6500, also you can run this command. If you have VSS box, means you have single control and dual data plane, you can check show redundancy. Likewise, behind the scene means the architecture wise, we have two CPU, CPU 0 and CPU 1 for a single line card. So suppose this is my line card 1, it is mapped with two CPU. You can check even with the particular line card as well. If you type this command show redundancy, you will find that one box is having the primary CPU. So you can see CPU 0, 0, sorry, CPU 0, 0, 0, 0, 0, and other side also you have CPU 0, but you have RP1, RP1. So you have RP0 and RP1. So they are redundant in that fashion. So one is primary, one has the backup. I skip one slide. Maybe I'll come back on that slide after some time. They have tuned some features of BGP in this particular platform. And if you go through this particular slide, will come to know that if BGP process will crash, it will not impact the entire operating system. Like in normal operating system, all the features are embedded. But in this, because they are XR platform and they have independent process call or procedure call. So if one process, say in this example, if BGP will crash, it will not affect the other processes. So BGP will make crash and they will switch over. You can see here NSR process failure switchover. So it will switch over from RSP0 to RSP1 and will feel that BGP has crashed, but is still there is no impact for the traffic. So BGP process, if BGP process crashed. That is a good question. Any feature may crash like OSPF or no, the router will crash, that is different thing. Inside the router you have operating system is hosting different daemons like OSPF daemon, RIP daemon, BGP daemon. So there are chances that any of the process may crash. Now what will happen after crashing of that process, that is different thing. But there are chances any process may crash. Okay. And more on the same case. So this is again very important slide. Now when I configure this lab topology, you'll come to know that while we are doing the configuration in normal iOS, how you are doing. So we are writing something like router OSPF1. Inside that we have router ID, we have network command, something like that. In this case, they have removed this type of structure. So once you are in the router OSPF process, then you need not worry about all the network commands and all these things. That is the one thing. Second thing, like ASA firewall. In ASA firewall, you don't have this IP keyword. Means you're not writing show IP route or show IP interface brief. You're using show route, then the feature. So like that in ASR as well, you have this thing, show route and then the feature. So show route OSPF show route, BGP show route is static, like that you have to check. So they have removed the IP keyword, even show access list, like something like that, show BGP summary. So they have removed that IP keyword from this.
If you are not using network command, how that particular subnet will be advertised in OSPF?
Okay, so what happened in normal networking thing, that when we are advertising, suppose this is my router, and when you are advertising the network, so what you are advertising basically, you are advertising the connected routes. So these are the connected routes you have. Means these associated interfaces have the interfaces have connected networks, and those networks you are advertising. So what we are doing in this particular platform, that we are advertising the interfaces instead of advertising the network. Okay. Okay. Go to next slide. So okay, the second command you want to check is this. And this is a big topic, software maintenance unit. For that, I have added some notes here by the bottom. I'm not going to read all these things. You have to go and read through this. But one difference here, you can see here, software maintenance unit, that in this particular platform, say suppose 4.2.3, if they have fixed some major type of bug, they have added here in the image itself. So this image has fixed this image has fixed this, something like that. Okay. This software maintenance unit, because this is Linux, what happens generally in Linux, that you can add some features in terms of, I don't know, API or something, but you can always add something in the Linux core. Like that in this also you can add something all the time. So you can fix the patches, something like in Windows also we are fixing some patches. So with the help of command line, you can fix the operating system. You can add some patches in Linux, in Nexus iOS also we can fix some packages. Like that you can fix it. Please go through this slide if you want to upgrade. You can upgrade if you want to do ISSU with respect to SMU. You can do that. All these things you can do it. Do that. Here I have given one link. If it will not open, please ping me. Okay, these are the links for SMU. Okay, please go through it. It's not very difficult. It's simple, normal iOS upgrade type of thing. But be very careful when you are doing it. There are several steps to do it. You can do it. If you have any problem, please ping me on this portion. Again, you can see here there are some mini and optional images. It's okay. I'll come to this software packages. Okay, it depends when you are doing the. Okay. These things I will show you in the lab. So in the PPT you will find for all the protocols like this. This is example with respect to OSPF. So OSPF, all the commands are there in OSPF. So how you can configure it? So you can enable router OSPF. If you want, you can enable the non-stop forwarding. Otherwise, the next thing that you have to define the area ID. Again, this is like ASA firewall also, you have to define area ID. Then you have to go inside the area. Inside the area, you can call different type of interfaces. So it's something like programming that where you are calling different objects. So you have area object. Inside the area object, you are calling interfaces. So this call is something like inside OSPF function, you are calling area. Inside area, you are calling interfaces, and then you are closing the program, something like that. So that is the good thing about ASR, that whenever you are doing any type of feature, like if you are doing LSCP, if you are doing OSPF, BGP, all the commands are under same under main program. So you have to call all the programs into the main program, something like that. You'll come to know in the example section. Here I have added some programs, some features or some protocols. So ISIS, you can see here how you can enable the NSAP address with respect to ISIS. But again, you have to call the interfaces inside the ISIS. BGP, maybe in the upcoming days, I will discuss L2 VPN and L3 VPN with respect to BGP, and plus MPLS. How MPLS is doing their LDP level distribution things and level forwarding. So I will discuss it in future. Now with this particular router, the main use is BGP and MPLS. So because you know that ISPs, they are using BGP, and they are using all these features related to BGP. Like in BGP, you have address families. You can see on your screen that these address families are belonging to maybe IPv4 or IPv6. So we have IPv4 address family, we have IPv6 address family. Apart from that, we have different address families. So we have address family related to VPLS. We have address family related to multi-destination tree. Okay, so you have to call BGP. Inside BGP, they have added so many address families. You have to call AFI or SFAI, and inside that you have to do all the configurations. So we'll see that BGP things in upcoming sessions. This is really difficult in ASR. They have removed the feature called route map, and they have added something called route policy language. You can see here this is 100% programming, and in the oh yeah, please do not ping me. So you can see here this is the logic if and if else, and Okay, you can see this in your screen, that this is complete purely programming language, and I have actually 2 to 3 hour session on this only. Route policy language. So it will take some time to understand the construct of this, that how we can build a, in other words, the route map policy, but in the ASR terms, this is route policy language. And why they have done this? Because mostly on ASR router, expectation is to run BGP. So if you see this command, you'll come to know that everything is related to BGP. But it's like simple C programming when you have if and else if. So if this will happen, it's okay. Otherwise, this, like that. So else if, else if, else if, and then you have to call this function. Now, one major difference between the normal routers and this platform, that if you will not use route policy or route language, policy language, your BGP will not work. So you have to attach something in the BGP when you are configuring this. Otherwise, BGP will not advertise or receive the network. That means you have to learn this. Yeah, you have to bind it. Yeah, that's correct. Yeah. Okay. But yeah, once you'll start doing this, you'll find it easy. Let me go to the next slide. Okay, and there are some other things as well that we need to learn the regular expression as well. That is another headache. Okay. Okay. Anyways, these are the things that you have here, and some notes are there. Please go through this. This is the BGP notes, that it is now mandatory for XR to configure inbound route policy. Otherwise, no prefix will be accepted. So you need something to attach. Otherwise, it will not work. Okay. This is one feature of ASR, because this is aggregate router. So you can do the multi-link feature that is in the normal iOS. Here you can do it bundle. In Ethernet world, it is something like port channel or ether channel. So this is the configuration for bundling the links, and you can use either active, means LSCP active, or passive. If you don't want dynamic negotiation, you can use on. So it will be on for all the time. So bundle feature is there, that you can bundle different type of line cards, and obviously you will bundle the same type of line cards, and this thing you can use. Now I'm going to start lab on this. I think till this point everything is okay. So once I will cover the lab, after that I will go to the architecture of this platform, and I'll show you this is the architecture. You'll find it easy once you understand this. This I have covered, and this is the routing process. Will come to know. So I will cover all these things. Let me start the lab, basic lab on this, and then I will come and do all those things. Oh, where is the workstation? Okay. Are you able to see these devices? I can maximize it. See. Okay. So I don't know how to maximize. It's okay. Okay, so I have devices R1, R2, R3. Username and password are Cisco. You can also have these things on dcloud. dcloud.cisco.com, you can have this. Okay, I am on router number 1, and I think that is visible there. So you can see there. What I'm going to do, I'm going to assign one IP address here. The IP address assignment is a bit different. It's like Nexus type of assignment. Suppose I have gig interface 0000 4 times 0, and there I want to assign IP address something like 10.1.1.1. Parallelly, I'll show you the topology as well, otherwise it may be confusing. This is the topology. So here on this this is gig 000, this is loopback 1 slash 24. If you are giving 255.255.255.0, it will take it. No shut. If you check the configuration, with the help of show configuration, it will show you the uncommitted configuration. Once you commit it, now it is committed and the interface is up. Now if you check do the same thing we are using in the, now it will tell that IP is not working there, but still it took IP. So you have to output with IP, without IP. You can check the interfaces. Let me go to other interface, that is the loopback interface 1, and assign one IP 11111 slash 32 and commit it and do show IP interface brief. If you want to create aliases, you can create it. Now I have two IP addresses on R1. I'm going to R2 and I will do the same things. So username and password are Cisco. Cisco and Cisco. The same conft and then the host name I'll change. So host is R2. Interface gig 0000 has IP address 10.1.1.2 here. Loopback 1 has IP address something 22222 slash 32. It's a bit slow connection. Okay, 2 slash, I already typed, still it has to come. Okay, so what I will do, I will type it and I'll wait for some time. Dot 2 slash 32. Okay, then commit do show IP interface brief. Do show IP interface brief. Sorry for typo. So now I have IP addresses. Now if I want to ping from here, again the ping is again normal. You can ping from router number 2 to router number 1 and I'm pinging. Now the routing protocols are different, means the functionality is same but the configuration is different. So what I'm going to do, I'll show you the static route, how you can configure the static route, and then I'll move to RIP, OSPF, not RIP. So suppose from here if I want to create a static route and I have this topology. So what I want to do here first, that from this router number 2, I want to create one static route for this loopback. So obviously the next hop will be this and it is going to reach here. So let me do that from the CLI. You can do IP route in the normal iOS. Here it will not work. So IP route, and in normal iOS what was the command? So you will do 1111111 something, then 255.255.255.0 and then you will give the next hop. So next hop is this. But here this command is not supported. It is supported, you may kill me. But here we are not doing like this. Okay, so how we are doing this? First remove it or uncommit it. You have to go to router and then static. First you go inside that protocol and then you define, see you have, even let me do one time exit. See here very carefully, this is a difference in the normal iOS and iOS XE. So you have to type address family and you have to specify, is this IPv4 or IPv6 unicast address family. Now here I can press enter or I can continue here. I have both the options. So I am going to do, I am continuing here 1.1.1 slash 32 and then the next hop. So next hop is 10.1.1.1. Now if you check show configuration, you will see that address family IPv4 unicast. I have done no with that the first command. Now because both the commands, you can see both the commands are supported there, but they are removing all those old commands. Even if you type show IP, if you go to interface and you type show IP IP address and then the IP address and the subnet mask, it will take, but you can use slash notation. Now you do commit here, so let me commit, and once I will commit, then I will check the reachability. So I'll wait for the network to come. Okay, so it is committing. So once it will commit, I will ping to the destination, that is, I have some network issue. Then I'll ping to 11111 network. Okay, so we'll wait for some time, and while I'm waiting, I'll do I have, no, I don't have connectivity. Sorry for that. I'll pause the recording as well. In the meanwhile, if you want to, so let me go through the architecture of this ASR. Here you can see this is the overall architecture of this platform. So you have two parts in this platform. You have something called the line card or the IO modules. So these are the IO modules. This is 40 into 1 gig E IO module. This is 8 into 10 gig E IO module. This is 4 into 10. You can see this 20 into 1. This is the backplane. Now from this IO module, we know that we have two traces towards the core. Two traces means one trace is going here and one trace is going here. So for all the IO modules, one is active, one is a standby. So one RSP is active for this line card, one is a standby for this line card, and you have this orange and green color for that. Now inside this ISP, inside this line card, let us focus on this line card. So you can see here we have SFP port, 10 gig SFP plus. This SFP is connected with the network processor engine NP. This NP is again connected with the FPGA. FPGA is nothing but the baseboard that is termed as a field programmable gateway array, something like that. So SFP, NP, FPGA, and that is connected with the ASIC, that is Octopus. If you know the Nexus architecture, the same Octopus ASIC is used inside 7K and 9K. Again, they are mapped with the backplane, and they are going for their control packet. They are consulting the RSP. So they are consulting in this way, and they are consulting in this way as well. Likewise, you can see in the other line card, that is 8 into 10 gig line card, two of the interfaces are mapped with one process. That is the network process, and they are centrally mapped with the octopus. In the 4 into 10, so the bottom line is this: whenever you are moving towards high speed gigi interface, at that time single interface will map with a single ASIC. So whatever interfaces you have, they are mapped with the specific ASIC. So suppose in this case you can see this is 10 gigi ASIC, but this is 4 into 10 gigi. It is mapped with single NP. Then they are mapped with the octopus. That is the central ASIC. If you have suppose 100 gig eASIC, they have a say interface, they have a specific ASIC, and again they will map with the central ASIC that is going towards the fab module or whatever crossbar you have, the central crossbar. So this type of structure you have overall for all the devices. In this case, what is special in this case? In this case, you don't have active and standby type of supervisor that you have in Catalyst 6500 or maybe 8500. Instead of that, you have active hardware and you have a standby hardware. Now I'll come inside this RSP unit as well. In the RSP, you can see again you have different type of ASICs. So you have Santa Cruz, and again you have Octopus. I don't know about this Bellagio, but these are the ASIC, Santa Cruz and Octopus, and they are mapped with the CPU. So overall, what happens if you see any type of architecture, you have something called central processing unit. That central processing unit will be mapped with some memory. This central processor unit will be mapped with some flash or fast memory, something like RAM or ROM. Now in the modern switches or these type of architecture, what you have, that all the interfaces you have some dedicated buffer memory. So these dedicated buffer memory, maybe you have inside the ASIC, or maybe you have centrally somewhere. In Nexus they have centrally somewhere, maybe SOC or something, switch on chip. But here maybe it is inside NP or FPGA, I don't know about that. But all the interfaces you have some buffer, and those are again mapped from one ASIC to central ASIC. That is the overall structure here with this device. Let me go next. Okay, this I have already discussed. Now, this is again very important to understand that we have two paths, normal path and punted path. Punted means that is punted towards CPU. This is the packet path snapshot or something. So from one line card, say line card 1, I'm moving to line card 2. This is the normal path. If you are tracing, if you are doing some sort of troubleshooting, you may have drop here, you may have drop here, you may have drop here. We can't go after this. Say in Nexus and in Catalyst 6500, all the interfaces are mapped with some ASIC. So whenever we are taking ELAM capture, maybe you know about this embedded capture, we are sending one packet towards the ASIC and we are capturing through that. In this case also, I will give you one list of command where you can come to know on which particular NP the packets have some errors. So we don't have any specific packet capturing towards NP, but yeah, we can come to know if latency is there, if packet drop is there, if network disruption is there. Inside that box, we can run those commands and we can come to know. I have one list of command I'll give you that you can trace up to NP, that any drops are there, any errors are there or not. If anything after NP, that is purely hardware, we have to change that particular slot. So you can see here that by default their tendency is go like this, but if they are doing first time, they will ask to CPU, so they are asking to the core or the RSP. Once they get information, again they are writing those informations into the line card, and they are going like this. So NP, FPGA, Octopus, backplane, and then again you have Santa Cruz. This is the RSP 0 or 1, either active or standby, and this is the packet path inside the hardware. This is again very important slide. So what is the order when the packet is coming inside the interface and when it is leaving the interface? So these are the checks checks when the packet is coming ingress, and these are the checks when it is going out. Now, ingress and egress, you can know this thing that QoS, whenever packet is coming inside, at that time you can do the software QoS. When it is going outside, it's very difficult to apply the software QoS. So that's why we have hardware QoS when it is leaving the interface. Now, this is the order: interface classification, ACL classification, QoS classification. So these three are classification. They will classify the packet, then they will check their safe entry, means they will do the fib lookups, then they will apply the ACL action, L2 read write operation, and QoS option, and then they will send the packet to the egress. So from ingress the packet will move to egress. Again, when the packet will move to egress, again read write things will happen. So they will change the layer 2 information. They can change some, maybe I don't know, they can change the ether type as well. They have to do some changes, and they will see that do I have ACL applied in the egress, do I have QoS applied in the egress, do I have to take action for the ACL in the egress direction, do I have to take any hardware QoS action in the egress direction, and then the packet will move to the wire. So again, these are the things are very important. So when we are taking the ingress capture versus egress capture, we can check all these parameters. Okay, and these are the things, just you can go through it, how many MAC addresses a particular module can learn. This is again more about the RSP. So how all these things, and some of the things we know already here, that what is Octopus, what is Santa Cruz. So these things you will get here. This is the interface. If you see this, you will find that, oh, I have console that I can connect RJ45. I have LAN RJ45 connector. You will find some LED status here, and how these things are mapped with FPGA. That is the baseboard. Actually, this is the baseboard, and how they are mapped with the CPU, central processing unit, and what are the different buffers you have. So DRAMs, how they are allocated. This is exactly the top view of the chip. So if you see that RSP2 in the top, you have all these things, and finally they are mapped to the backplane. You have Octopus, you have Santa Cruz, all these specific ASICs. This is again the line card architecture. Let me go through this line card architecture. After that, I will not discuss any architecture. Okay, so at least we know that we have interfaces. So interfaces are mapped with NP. That is the network process engine. That NP is mapped with FPGA. That is the field programmable gateway array. Those are mapped with some ASIC, maybe Octopus, and again they are mapped with the central ASIC. And those central ASIC, they will send packet to the backplane. So this is in this direction. So here you have the interfaces. You can see interfaces are mapped with NP1, 2, 3, 4, 5. These NPs have their own TCAM. They have their own buffers. You can see here. And they, yeah. See, one port is mapped with one NP. So it depends upon which type of line card you have. Sometimes you have dedicated NP, sometimes you have this group of ports will map with uh, some ASIC, and that is true. If you work on some switches, you'll come to know if you are using interface range command with some range, it will throw an error. Why? Because some of the ASICs are not mapped with those interfaces. Those you are taking the range command. So suppose 1 to 8 are mapped. If you take range 1 to 9, it will throw an error. Again, these NPs, you can see these NPs are mapped with Octopus and then your baseboard processor. So this is the last slide for the architecture. I don't want to discuss this, but you can refer it. If some module failure or some line cut failure or some supervisor failure is there, so we can refer this thing where it is the failure, because whenever you have log message, clearly it will show that NP is failure or something is wrong in the line card. This I already discussed, and again you can refer this NP and FPGA, how they are RP2. This already I discussed. BGP, I need two at least, two sessions to complete BGP and MPLS that I will cover up in upcoming days, and one for the route policy language. I hope that we have network connectivity. Let me check that. Someone has blocked our. No problem. And that is the good thing about dcloud. I can restart the session from there. Yeah. Copy and actually problem with this, I think. Let me close this. Okay, I'm pausing the recording for a moment. I have all the devices and I'm going to configure OSPF on R1, R2, R3, R4 according to our topology. Somewhere we have topology here. Same, I'm going to use username Cisco, password Cisco, because I know you can change the hostname. There are some commands in this ASR router that you have to use the admin keyword and then you have to write those. Would you like to proceed in configuration mode? Yes. Okay. Host R1, interface loopback 1, IP address. I'm going to configure it fastly. Then interface gig 0000, that is the pane 4 times 10.1.1.1/24 no shut commit. Okay. Now if you want to enable OSPF, you have to do like this, router OSPF, and then you can give number or name. So suppose I'm giving name as a test. Then you have to define router ID. On R1 I can define 111111, and then you have to go inside the area. So this area is in area 10. Interfaces are gig 0000 and other interface is loopback 1. If you check show configuration, this is your configuration in the programming language. So you have the main procedure, that is the OSPF. Inside that we have router ID. Then inside area we have loopback 1 and loopback 2. If I okay, I'll do the commit. exit. If I type area 0, I'm inside area. So what are the options you have in the area? You can see you have enable BFT, you have uh, option for authentication key, all these things, the same things that we have in the normal iOS, except this route policy. This route policy is a bit different in this domain. On the other device as well, we can use Cisco. The host is R2, interface gig 0000, IP address is 10.1.1.2, loopback 1 has IP address /32, and I have one other gig interface that is going from R2 to R3. So this I have configured, this interface I am configuring, that is gig 0001. Gig 0001, sorry for that, gig 0001, and IP address is 10.1.suppose2.1. All the time I have problem with R2. Yeah, but still I am able to log to it. Yeah, okay. Then we can do no shut and we can commit. Once you are committed, we can enable OSPF. So here also you can type router OSPF. The process is the same. We move to the OSPF process. Now we can define the router ID and then the area. So I have two area here. I have area 10 and 0. So one interface will be in area 10, that is gig 00. So let me do this thing. Area 0 has interface gig 0001 and interface loopback 1, and inside area 10 I have interface gig 0000. Okay, now I have to commit it. Let me configure R3 and then I'll come back. Host is R3, interface gig 0001, 10.1.2.2/24, loopback is 1, IP address is 333/32. Commit router OSPF test. Router ID is suppose 3333. Area 0 has interface loopback 1, interface gig 0001, commit. Now we can verify this on our router number 1. So we can check show run, and if you check the options, we don't have section that is there in the normal iOS, but we have begin, we have include. So if I begin with OSPF, so it is showing that this is the command for the OSPF. The router ID inside area, actually we have two areas here, area 0, area 10. If I check show, I can't type show IP route and then OSPF. You can do it actually, but they have removed this IP keyword. So the basic command is, if you are not able to write in the actual hardware, I don't know, but here we are able to write it. They have removed this IP keyword. So this is the way that we can verify. Apart from that, we can check show IP OSPF never in the normal iOS. Here you have to check show OSPF never. Okay, so DR formation, because we are using point-to-point links, that's why it was committed, I think. Okay, here also we can check show IP OSPF neighbor. Actually the command is show IP, show OSPF neighbor and OSPF neighbor and show OSPF database to check the topology table. So functionally you can see everything is same, the command and syntax are different, and that is the example with the OSPF. Now I'm going to show you one more example that is actually very important example, and it's very different in this platform. That is how you can bundle the interfaces. So if you want to bundle the interfaces, it is somewhere in this slide, maybe by the end of this, or yeah, this is, yeah. So how you can bundle the interfaces? First you have to enable one interface name. So in normal Ether channel, it is different when you are doing in the switch. Here it is very different. Even if it is different when we are bundling the serial links in the routers. At that time we are using interface multi-link. In this case it is bit easy. So let me show you that bundle interface. Suppose I am bundling between R2 and R3. So I am showing you just the how to bundle it. Interface bundle. If I type question mark, you can see here we have two options. One is POS, one is Ethernet. POS is nothing but, what is that? Power over Ethernet, SwitchNet, something. This is related to Sonnet interface. So if you have some Sonnet interface, you can use this bundle Sonnet. Ethernet ID you have up to, you can check. You have to type E here and then question mark. So it will show you have these many numbers. Suppose I use 100, and then all the keyword will start with bundle. So max link active, how many link you want. Suppose I have 2 maximum link. Then how many minimum active link you want. Suppose I have 1. If you want, you can give the hash algorithm as well. So what is the load balancing algorithm you are going to use? Is it the source IP based or is it the destination IP based? Suppose I use source IP based. After that, you have to go to the certain interface. So suppose I am going to gig 0001, and here you have to add this particular interface into the bundle. So bundle ID is 100, and what is the mode? LACP mode. Suppose I can use active, and the most important thing that you have to do the commit. It is failed here because this is not the order of operation that I have used. So the order of operation is that you have to define a bundle, then you have to define IP address on that, and then you have to do all these things. After that, you have to go inside the interface, physical interface, and you have to tag that physical interface with the bundle. So if you will not do this thing in the particular order, that will throw an error. And it is showing that, yeah, you have this error. If you type this command, that is the show configuration failed, then it will show you that what error you have on this interface. So that is also important, that if you are doing something wrong in the wrong order, the iOS will not take it. Okay? Same type of configuration you have to do on the other side as well, and then your bundle will form. Okay, so that is it from this presentation.